I think it's recording now, so I will start the class. Hmm. You guys know what is ordered, I believe, like, right? Anybody? Or should I tell the definition for
Yes.
order? Okay, so what are primitive roots? Like, we know that for some number a to the power k is 1 mod p, and k is the smallest integer. This is the order. So for uh, some values of a, we get this k is equal to p minus 1. Like for the Fermat's last theorem, we already know a to the power p minus 1 is 1 mod p, but this becomes like the least integer also in this case. So for those a's, uh, we'll call these numbers primitive root modulo p. Uh, any issue with the definition?
No.
Nice. Okay.
Can you
We'll
repeat once
normally,
more? I joined just now.
yeah, I just defined what are the definition of primitive root. Do you know that?
No.
Okay. You know what is order?
Yes, sir.
Okay. So a to the power k is 1 mod p, where k is the least integer, that is order. And when this order is equals to p minus 1, for those a's, we call that a primitive root modulo p. Is that clear? Like we know that order divides p minus 1, but when it just equals p minus 1, those numbers are primitive root.
Okay, yeah, good.
Nice. Normally, we call primitive root as g if you see a problem. Like I write g and I don't define, think that as like primitive root. Uh, I'll just paste the easy lemma, then I will do the prove that primitive root exists. Like we don't know that this number exists. Like there will be some order which is equal to p minus 1. So we'll prove that after doing a lemma. I'll just paste it. My content. Control V. Okay. So try to prove this. If g is a primitive root, uh, if g is a primitive root, then uh, like basically g to the power 1, g square, g to the power p minus 1, this covers the whole residue system modulo p. And this is the
there any
basic
buffer?
reason we use g. Yeah,
Is there any buffer?
there are buffers. I'll just paste the buffers. Give me 1 minute. Those guys who haven't like seen this before, try this. I'll just paste the buffer problems. Okay, I'm giving one buffer now. If you guys solve it, I'll paste another one. Take a screenshot for this. And if you're done with this question, wait. If you're done with this question, then try for any integer, not only square free.
Is
Like
that
I
a
made this
minus
square free
sign?
to make it easier. This is the minus sign.
Okay.
A to the power a minus b to the power b covers the whole residue system mod d. Did you take a screenshot or like write down the problem? I'll just move it then.
I
A
didn't
and B are
understand
fixed or what?
Yeah.
No, you can move A and B basically. That is the point. And C and D are fixed. And you can do Find A and B such that this holds.
Oh,
They
prove that they
exist A and
exist.
B.
All right, fine.
I'll just come back to the lemma. Try this. Any idea on how to approach like those guys who haven't seen this before? Anyone? Okay, see. So what do we have to prove? That this covers the whole residue system mod P. So if we prove this for some g to the power I and g to the power j, where I not equals to j mod p minus 1 basically, mod p, like this can't hold, then we are done. Because then g to the power 1, g to the power 2, dot g to the power p minus 1, and all the powers p minus 1 mods are different. So they all will give different residue. So try to prove this, that if I not equals to j mod p minus 1, then we will have g to the power I not equals to g to the power j mod p. You have this, and you want to prove this. By the way, is the pen color too thick? I can make it a little lighter. But I am probably too zoomed in. I don't know which one is true. Let's try this. Anybody? Why can't this be true? Like why this is true?
Otherwise, like the order is less than p minus 1.
Exactly. So we'll have like without loss of generative, we'll assume I greater than j. So just divide it both the sides. G to the power I minus j is 1 mod p. But because this is the primitive root, we know that I should be j mod p minus 1. But both of them are less than p minus 1. So this can't be true. This is a contradiction. So we get this. Did everybody understood the proof?
Yes.
Okay, nice. So basically, this is the whole reason we use primitive roots, mostly because we'll have any say like t or something, and if we take a primitive root g, we can make that g to the power I, and sometimes making some number in the power helps doing some questions, which we'll later see in problems. This is the basic idea on why do we need primitive roots.
It can we guarantee that every prime has at least one primitive root?
Can you repeat again?
Can we guarantee that? Can we prove that every prime has at least one primitive root?
Yeah, I'll prove this. I'll right now prove this. Okay, for this proof, I'll need a lemma, and I'll just paste it. Mm, You guys should try to prove the lemma. It's not too hard. So you know the like if some polynomial px is of degree d, then it has at most d roots because it can have like repeated roots, so it has like less than equal to d roots. You have to prove that this is also true when you take the polynomial in FP. What is FP? Think of it as like all the coefficients of the polynomial are reduced in mod P. So everything is in the polynomial is reduced in mod P. So every coefficient is less than equal to P. Not less than equal to, less than P, because if it is P, you can make it 0. Every EI, where EI is the coefficient, is this. So you reduce the polynomial FP, and that also has like only D solutions in the congruence class. At most D. Try to prove this. When D is greater than equal to 1. Did everybody understand the lemma? Not the proof, because I didn't discuss it, but the statement of the lemma. Did everybody understood that?
Yes.
Nice. Okay, I'll give you a hint. It's kind of motivated. Try on induction. Induction on D.
Can you explain the lemma again?
Sure. So you have fx, a polynomial in Fp. Did you understand what is Fp?
No.
Fp is where all the coefficients basically of the polynomial, all the coefficients of the polynomial is reduced modulo P.
Okay.
So I'll give you an example. Something like x square plus 17x plus 13 mod. Say this is in like F5 basically. So this will become like x square plus 2x plus 3. Okay.
Yeah.
Like you
Okay.
take everything mod 5.
Okay. Then
Then you have to prove that if the degree of the polynomial is D, then it has at most D solution in mod P, like D congruous classes of mod P, at most. Like you know
okay.
that if a polynomial
Yeah.
in general has D degree, then it has D at most D solutions. Here it is like not a polynomial, it's just a polynomial FP, like all the coefficients are reduced modulo P. Still, the Lagrange thing does hold. Try inducting
Okay.
on
Got
D.
it. Thank you.
That is a hint. So for induction, what do you need at first?
So we just need to prove that we can have one root.
I mean, like, if you are doing induction, what you should do first to, like, what is the main step of it? Not the main step, what is like the primitive state of induction?
So
If you're doing it,
we could consider a root if it exists. If the root does not exist, then we are already done. And if a root exists, then we can factor that root out and get a polynomial of DVD dimension.
exactly. That is the main part of the proof. But I meant the base case step, basically. So for induction, we need a base case. Here the base case is d equals to 1. It's quite obvious why d equals to 1 is 2, but I'll just highlight a point that that somebody can miss. Like ax plus b, this is 0 mod p, right? So we'll have like x is minus b by a mod p.
If A
If
is
like
A is co-prime
if
to
a
P.
is co-prime, if GCD of a and b, not a and b, GCD of a comma a.
Like if P divides A, then like if we, because we are reducing mod P, it would just become 0 now. So there would be no solutions.
Exactly. So
B
if
and A
p
both can be
divides
0.
a, and we need like p to divide x plus b. Like if there is any solution, then p also has to divide b, and we know that p also divides a. So this fx actually in fp is 0.
I mean, like A cannot be 0 mod P because then the degree would not be 1.
Yeah, that's
So
what
A
we
is
meant. The
obviously
degree should be greater than equal to 1, but degree is not 1. So that's why it can't hold. P can't divide both the things. So we just get that there is at most one solution. If p divides a, then there is no solution. And if p doesn't divide a, then there is exactly one solution. I hope the best case is clear.
no, P cannot divide A, right?
P can divide a. P can't divide both a and b.
No, P cannot divide A because like we are working in FP. If P divides A, that would mean that A is 0. And it's like obviously contradiction to the degree.
Okay, it's true. P can't divide a, then the degree is 0 in this case. Sure. Yeah.
Also, like if we find a root, how can we factor it out mod P in the sense?
Yeah, I'll
Yeah.
just tell that.
Factor theorem
So
holds in FPX. We should prove that.
mhm.
Like just we prove how we prove factor theorem in RX. We could prove that in FPX.
Yeah, like we can factor also in like FP, not only in our normal thing. I'll not prove that, but you can look up the proof. Say T is like if there is one solution, because if there is no solution, then 0 is less than D. So we just take T to be a solution. So we know that FT is 0 mod P, right?
Yes.
Okay, now consider the polynomial fx is equal to something like
X minus T times some other polynomial, right?
ei to the power xi. I mean, just like how you consider polynomial, where all ei's are in 0 to p minus 1, I equals to 0 to I assume the degree to be D. So like in our base case, like we have done till D and we are inducting on D plus 1. So I equals to 0 to D plus 1 because fx is now on D plus 1. So what we basically do, the factor theorem that he is saying, fx minus ft this is summation of I equals to 0 to D plus 1 will become like ei x to the power I minus t to the power I.
Yep.
Okay,
And you can factor X minus T out.
exactly. So if we factor x minus t out, because we can factor, and you will get some polynomial. See, this is like a D plus 1 degree polynomial. We factor x minus t out, so it will be a d polynomial, like polynomial with a degree d. So we just write that as gx, where gx is a polynomial in fp.
Now you're like basically done because
Yes. In fp with a degree d, and by our induction hypothesis, we know this has like at most d roots, and this only has one root basically, because if fx is a solution, we need this to be 0 mod p. So either this is 0 or this is 0. If this is 0, there are d roots, and this has at one root. It can happen that this one root lies on this gx. In that case, that will be strictly less than. And if it has exactly d roots and the new root does not lie on gx, then we will have like exactly d plus 1 solutions. So
we are done.
basically we are done with the theorem, basically Lagrange for fp. Any issue with the whole proof? Any part?
It's clear.
I think it's
Okay. Okay. Now I'll prove that. Just I'll paste it 1 sec. We'll only prove for like p and p to the power k basically, but you can see that we can prove all of them. Like 1 to 4 are like, you can just see, and we'll prove that after 2 to the power k, there exist for n equals to 2 to the power k, where k greater than equal to 3, there can't exist a primitive root. And other things we will not prove right now, but at first we want to prove that for p there exists a primitive root, the main thing, because in 99% cases we only use that for p there exists a primitive root, p when p is a odd prime. So try to prove that like the Lagrange thing right now. So try to think of a polynomial in fp which can help in this case, which fx px, let's say, equals to what can help for proving primitive root modulo pre. Now we are discussing only p. We'll any guess which px can we choose? What should be the best? Take 2-3 minutes. Try to think of a polynomial where has exactly p roots, like it should have less than equal to p roots, but try to think of something which has exactly p roots with a degree
like,
p minus 1.
you mean like x to the p minus x, which has x into x minus 1 dot 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 till x minus p.
Yeah, but with a degree p minus 1. So what does that poly becomes?
X to the p minus 1 minus 1.
Exactly. So we take this, and by Fermat's little theorem,
This should
like for every 1 to
p minus 1.
p minus 1, there is a root.
Yeah, so those are exactly the p minus 1 roots.
Exactly. Okay. Now try to prove that say p minus 1 is like AB. Okay.
Okay.
Try to prove that x to the power a minus 1 also has exactly a roots in FP.
What is A and B like? You're randomly factoring it into two numbers.
Yeah, randomly factoring into two numbers.
Okay.
What should we prove again for x power a minus 1?
That it has, I'll write there, that it has exactly a roots in FP.
Okay.
Like we know that for P in FP, it has exactly like P minus 1, it has exactly P minus 1 roots. Now we want to prove that every factor of P minus 1 also has that.
I mean, this is just trivial by primitive roots, right? Like A obviously has to be co-prime to
We
P.
are trying to prove primitive roots.
Yeah.
Oh, sorry, my bad. Whatever.
Do this. I mean, like I have seen people assuming something and then proving it. That's like funny. Okay. So what is the next thing we could do? Like x to the power P minus 1, this has like P minus 1 roots. Can we try to factor this polynomial?
I mean, x to the A minus 1 will obviously be a factor of x to the P minus 1 minus 1 since A divides P minus 1.
Exactly. So x to the power P minus 1, x to the power A minus 1.
Times
This
some other.
factorization will be like, let me think once. 1 plus x to the power B plus x to the
Power 2B and so on.
wait, not x to the power B, x to the power A till B.
No, it should be like x to the power B till AB, right?
No, like things should cancel out, right? Like minus 1 is here,
Achha,
then
okay,
plus
yes,
x to
yes.
the power A minus here.
Yeah, dot till x to the power AB minus 1. AB into B minus 1.
Yeah. And what are the number of roots for this polynomial?
Like this
Less than equal to
A
AB
into B
minus B,
minus
right?
1.
And
Yeah,
do
so
you know
that
that
has
this has exactly AB roots? And so this should have greater than equal to A roots because this is less than equal to AB minus B and this has exactly AB.
that's AB minus A, right? Not AB minus B.
AB minus A, sorry. Yes. So x to the power A minus 1 has greater than equal to A roots, but we also know that this should have less than equal to A roots, so that's why it has exactly A roots.
Yeah.
Do you see the proof? Nice. Any doubt with this thing? That why x to the power A minus 1 has exactly A roots? I'll assume there is no doubt. By the way, do you guys know this? In orders, I don't know if Manda told or not. If order P of some A is like B and order P of some C is D, that will imply order of PAC equals to BD if GCD of B comma D is 1. Basically, this is multiplicative if these two things are co-prime. Do you know this in orders? or should I need to prove this? Anyone?
I think this is done.
Uh, can anyone else say if like, okay, even if it is done also, do you know this or not? Anybody? Let me check the chat. I'm not checking.
Wait, can we prove this?
Okay, I'll prove. You can try for like 2-3 minutes. I'll
Okay,
prove
yeah.
it. It's not hard to prove. It's only ordered. So I don't think there is anything in the chat. I just go back. Any idea, guys?
Yes, chat is like mentioning the correct idea. We should use primitive roots to prove this.
That's a very good idea, but the issue is like we are proving primitive roots.
Yes.
Suppose like say x is the order, then like
Okay.
AC whole to the x is congruent to 1 mod p. So like a to the x is congruent to c to the minus x, and then you like do a to the x whole to the b is congruent to c to the minus x whole to the b,
Wait, what is
and
C?
then the
I got
LHS
the
is
idea. That's the correct idea. I'll just write it down.
Where is C
So,
over here?
can you repeat?
What
I
is
am.
C?
C is another number. Like this is C.
Oh, I
Or
thought that was an E. Okay.
Like that obviously looks like an
That is
okay.
an E, it's not a C.
Aritra, just write somewhere C equal to E, we can end this discussion there.
yeah, that would
I'll just not use C in today's class. This is the last time I used.
Wonderful.
Like I have heard this probably I don't know, Google number of times.
I've
Okay.
heard it more than that for
we should
you.
use M and N bro, like X and Y and NT just doesn't sound right.
I don't care. Okay. I mean, I can use M and M, but I'll just use that in the power. So we guess like we take x to the power y to the power m is 1 mod p, where m is the order. Okay, you are against x, y, and nt. Then bad luck just. Okay, xy to the power m is 1 mod p. From here, I think Riddhiman told we can do like x to the power m, y to the power minus m mod p, right?
Yes, we can. Not just raised to the power B, I guess, right?
Yeah. So we'll just raise like x to the power m.
We could just raise it to the power B initially. We did not need to do this stuff, right?
Well, like
And
we'll use it. That's why I wrote it. We can do like this is just manipulation. It's not NT right now. So
no. Like we don't need to do this. Like we could just raise the to the power B in the original equation x by to the m equal 1. So that would just give that y to the mb is 1. So that would imply that.
yeah, I guess that also.
but that doesn't imply like you got that divides, but you don't know if the order is exactly BD. Do you know that? It's You don't know if the order is exactly like you need both the sides.
Yeah, but
Like,
like y to the mb, since b and d are co-primes, that would imply d divides m, right? And b also divides.
mhm. Yeah, I
That
was
would
doing
give
that
that
thing only.
bd divides them.
Yeah.
And obviously bd does satisfy. So it must be the odd.
Aritra, can you repeat Sanskar's proof?
I'll just
No, like see xy to the whole to the m congruent to 1 mod p, just raise both sides to the power b. So x to the mb is obviously 1, and you have y to the mb is 1 by the equation.
xy to the
Okay,
power
so
mb is 1 mod p,
Yes.
and uh, in that we will also have xy to the power
so
md.
D divides M.
No, just to yeah.
So
Now
D divides M,
like
B
x to
divides
the
M.
mb is 1 mod p, so y to the mb has to be 1 mod p, and similarly that
Yeah,
would
so the
be
order divides like mb and md basically, right?
yeah. No.
Wait, what?
No, d
Order
divides
difference
mb.
is GCD of mb and md.
No. Like x to the y next to the mb would be 1 mod p. Thus y to the mb is 1 mod p. Since the order of y is d, so d must divide mb. Since b and d are co-prime, that means d must divide m. Hence, b must also divide m. Thus pd divides m, and obviously m divides pd.
Oh,
What
yeah,
is
okay, that makes sense.
I see.
Right.
what is MP?
B is like the order, and m is the order we assume. Like we want to prove that m is bd basically.
Yeah, x to the mb would just become 1 now. So y to the mb is 1, and d must divide mb, and since b and d are co-prime, d must divide m. Right. And similarly both
Hmm,
sides.
I see.
Right. I mean, we could just
Okay, I'll just do another proof for those guys who didn't uh, understand that. So we had like x to the power m is equivalent to y to the power minus m mod p, right? Now we can raise both the powers by, like he just didn't factorize it. I am factorizing it and then doing it. It's like same basically. I don't think there is too much difference with uh, what Sanskar is saying and what I'm about to do.
yeah, but
Yes.
like you switched x to k now. Like that's looking like a k.
This is K.
Yes.
How?
No,
I,
it's
I don't know.
U.
Like
Whatever, like this is isomorphic everywhere. So just think out of what you can
and
think
in
of.
fact this also is representing the mirror image of n. Like mirror image of capital N.
I think
I
it
don't
looks
know.
like an X.
Everything's messed up.
So we can just take it as like 1. So y to the power, like this is x to the power b, which is 1 mod p. So 1 to the power m is 1 mod p. So y to the power minus mb, this is 1 mod p.
Now just take inverse both sides.
So y to the power mb is 1 mod p.
Yes, so d divides mb.
No, so we'll have like d divides mb. Yeah. And as b and d are co-prime, d divides m. And we'll also have like b divides md. From there, we'll also get
D
b
divides
divides
b
m.
then.
So B, because they are co-prime again, BD divides M, and we can directly see like if you like 2 power D here, this is 1. If you do power B here, y to the power BD is also 1 mod P. You multiply, then xy to the power BD is 1 mod P. So the order is just BD.
Yep.
Okay. So back to the proof, like what we're actually trying to do. So we proved that x to the power a minus 1 has exactly a roots. Okay. Now I'll give you guys something. Try to think of that. P minus 1 equals to, say, we factorize it, prime factorize. P1 to the power a2, P2 to the power a2 dot 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 Pk to the power ak. Okay. So try to make all the orders like P1 to the power A1, P2 to the power A2 dot 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 Pk to the power AK. And then we can like do this thing because P1 to the power A1, P2 to the power A2, they are co-prime. Okay, like what I'm trying to say is, so there exists some x1s that like we'll prove that, and order of xk is exactly Pk to the power AK. Then if we just multiply, then all of their orders, that will just become order of some number, like all the xi's, order of P with all the product of xi. This is just become like all the multiples, so P minus 1. So this is a primitive root and we'll be done. So try to prove this, that we can get order some P to the power some Q, basically, like there exists x such that order P of x equals to Q to the power A, where Q is a prime and that divides P minus 1. And here you will need the Lagrange thing, basically. Try to prove this. Yeah, A is obviously less than equal to like the degree D. I also didn't get how did PP come up. Uh, Anyone, any approach on how to do this?
Wait, can you like repeat? Like what was the question?
Oh, did you get this xy to the
Yeah,
power PD is 1 mod P, right?
yeah.
So what I'm trying to do is find this xi's such that the order is P1 to the power A1. If we do this, then we can just multiply it and see like all the PI's are co-prime to itself. So they will just multiply. So we'll just get order of P for order of P, and while products of all the xi's is just a product of all this Pi to the power AI, and that is just P minus 1. So we'll get some number order is P minus 1, which is all we need for the primitive root.
Yeah, sure. So
All
like
right.
we can assume, suppose for a PI, we want to prove that order is PI to the AI for some PI. So assume
Work
there
with
is,
Q and A, like this is like for this, but you can work with Q and A. That will be easier because if we do for one, we can do for everything else. So we just have to prove that If
Yeah,
Q divides P minus, yeah.
yeah. So what I'm saying is that suppose there is not such X, right? So thus consider P minus 1 by Q. So everything, like every root must be, like every order must divide P minus 1 by Q. So X to the P minus 1 by Q has more than P minus 1 by Q roots. And that's a contradiction.
Can you repeat again?
Like, you just want to prove that, like, if VP of like VQ of P minus 1 is K, then there exists an integer such that order is P to the VQK, right?
Yeah.
Yeah, so I'm assuming. So yeah, so suppose there is like no primitive root. So since there is like no let's suppose there is no primitive root modulo P, because if there is a primitive root mod P, we are done. So if there is no primitive root mod P and there is no primitive root modulo Q to the A, then every root of X to the P minus 1 minus 1 should be like a root of X to the P minus 1 by Q minus 1, which is obviously a contradiction since P minus 1 by Q cannot have more than P minus 1 by Q roots.
Yeah, I got it. Nice. But can't this happen that like X to the power Q to the power A, this is like 1 mod P? Okay, I got what you were saying.
No,
Sure.
like P minus 1 by Q, since like any divisor of P minus 1 would not divide P minus 1 by Q only if the VP is like more than A. And if the VP of that is more than A, then that would imply there is a primitive root mod Q to the A. So that is obviously a contradiction. That means
did you get
So-
the proof?
so that means
Everybody.
either there exists a primitive root mod P or there exists primitive root modulo Pi to the AI for each I. So that would again imply that there is a
Yeah,
primitive root
that
mod
will
P.
finish basically.
Yeah.
Did everybody get the proof or should I explain it?
Can you explain?
Okay. He did with VP. I will not introduce that. Like what I will do is kind of his idea only, but write it in a different way. So, right. If you have X to the power Q to the power A to be 1 mod P, right? So order P of X, this will divide Q to the power A. So that means like the order lies in the set 1 dot 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 Q to the power like 1 Q Q square Q to the power A.
Direct Q to
And
the power A minus 1, right?
I'm not trying to prove contradiction. Like what I'm doing, you will get exactly there are phi of n. Basically like phi
Okay,
of P
you're not
minus
trying
1
to
roots.
contradict. Okay, sure.
Yeah. I'll just prove that there are how many things are there. Now see, if some order is some Q to the power I, okay. So X to the power Q to the power I is 1 mod P. We can just like where Q to the power I is the order, let's say, we can just power both the sides by Q to the power A minus 1 minus I, such that you get X to the power Q to the power A minus 1. This is 1 mod P. But how many roots does this have? Like this is a divisor of basically P minus 1. So you know that this has exactly, that's why I proved the exactly condition. This has exactly Q to the power A minus 1 roots. And normally we had Q to the power A roots, right? So in total, how many primitive roots will be orders will be there which satisfies this? Q to the power a minus q to the power a minus 1, which is just phi of q to the power a. And now we just multiply. So the number of things will also multiply because we can take each case and each case will get a valid result. So they are just the number of the things are just phi of this product of q to the power a, which is equal to just phi of p minus 1. So we also proved that there are exactly phi of p minus 1 primitive roots. Do you see the proof?
Yeah. Like if we get one primitive root, then obviously suppose like we get one primitive root, then all primitive roots are the ones which are like g to the power co-prime to p minus.
Yeah, I'll do
that
that right now
implies
only.
pi p minus 1 primitive roots if there exists one primitive root.
Can you repeat the last part of the proof? Since
Yeah, I'll repeat. I'll just copy something that people can
Also,
try and
Aritra,
I'll do.
like I think your proof gives there are like at least 5 p minus 1 roots, not exactly 5 of p minus 1
Oh no,
roots.
it gives exactly. Because we know that there are exactly q to the power a minus 1 roots, right?
Yeah.
And we know that the actual thing has exactly q to the power a roots because that's why I proved
Yeah,
exactly.
sure.
And that's why the total thing has exactly this many roots, right?
Yeah, like that's correct, but for the final conclusion,
No, for the final conclusion also we can say. Because like those q to the power a roots and q to the power a minus 1 roots all are distinct. So they are like q to the power a minus q to the power a minus 1 roots,
yeah, true.
which are primitive roots. And if you product all of them will be like distinct things. So
So
because
they will get, but like there could be some primitive root which might not be able to represented by a primitive product of primitive roots of q to the a, like p1 to the a.
no, if there is a primitive root, that will be a root of this. Like this has to be a root of this. For everything, this is a root. And
Okay,
we
yeah,
also
sure,
get
yeah.
oh,
Yeah, okay, yeah, it has to be a primitive root, one of those. Yeah.
okay. Somebody else was telling me to explain the last part from where exactly.
where you started with x to the power q to the power I can't get one.
Okay. Did you get till this? Order of px divides q to the power a, just the order thing, right?
Yeah.
So order lies in this set because q is a prime.
Yes.
So now let q to the power I be order, okay? So you have x to the power q to the power I mod p. And if you like do power like x to the power q to the power I is 1 mod p. And you do power q to the power a minus 1 to the power minus I in both the sides in power. So this will obviously become 1 because 1 to the power anything is 1. So that will make x to the power q to the power a minus 1 mod p.
Yeah.
By the way, you guys can try if g is a primitive root, then either g or g plus p is a primitive root modulo p square. Till then, I will explain this. And x to the power q to the power a minus 1 from the previous our Lagrange thing, we know that this is exactly q to the power a minus 1 roots, right?
But it's not a divisor of p minus 1, right?
Q is a divisor of p minus 1.
But q to the power a minus 1 is not a divisor of p minus 1, right?
No, that is a divisor. P1 to the power a1 is a divisor. Like q to the power, their power is a divisor.
Yeah. So, yeah.
Yeah. So because it is a divisor, it has exactly q to the power a minus 1 roots. And from here, we can also say that this has exactly q to the power a roots. So they are at exactly q to the power a minus q to the power a minus 1 roots, which are only only to this. So like they are basically their order is equal to this. And for everything, we'll have like this number of phi of q to the power a order. And if you like, because phi is multiplicative, you can like multiply all of them, and that will just give phi of p minus 1 roots. Did you understand this part?
Yeah, I think so.
Okay. Try this. If G is a primitive root mod P, then G or G plus P is the modulo primitive root modulo P square. Like for the sake of contradiction, you can assume G to the power, not Q. G is not a primitive root modulo P square, and you should try to prove that G plus P is a primitive root modulo P square. So we assume G to the power P minus 1. Like G is a primitive root mod P, right? So the order will at least be P minus 1. And we want to prove that this is not 1 mod P square. Like this is given, and you have to see the G plus P part.
I mean, we could just prove this by like g to the p minus 1 is not congruent to g to the g plus p to the whole to the p minus 1 p square, right?
Wait, just 1 second. I'll come back in 1 minute. Yes, Sanskar. What did you say?
Yes, so we obviously know that g and g plus p both are co-prime to p square, right? We obviously know that g and g, thus they must satisfy Euler's theorem. So we know that g and g plus p to the pp minus 1 is what do you say, 1 mod p square. Now, if we assume for the sake of contradiction that none of their orders is p to the p into p minus 1, so their order must divide p into p minus 1, but it must not be p minus 1. And obviously p minus 1 divides their order. Therefore, their order must be exactly p minus 1 if it's not p into phi of p square. So thus we must have that g to the p minus 1 congruent to g to the p minus
I see.
1, congruent to 1 mod
That
p
is
square.
what I'll also be doing. Yeah,
Yeah.
I got what you're trying to say.
And
That
that's
is
the
exactly
contradiction.
what I'll be doing. I'll just write that. So order this is just p minus 1. I am writing this. Or like G is a primitive root. So we'll assume order of p squared is some k, let's say. And because k is not a primitive root modulo p square, so one sec. What did I have to do here?
And K should divide P into P minus 1, right?
Uh,
Like you should.
yeah, K should equal either P minus 1 or P into P minus 1. That is what I'm trying to prove.
Mm, Yes, but like there's of
Yeah, so K divides like P into P minus 1, right?
yeah, K divides P
But
into
we
P minus
also
1.
know that
P minus
because
1 divides K.
yeah, because if we take mod P, we can take the same thing mod P, and we know that P minus 1 divides K.
Yeah,
So, so from here we get that K is equal to P minus 1 or P
times
into
1
P
minus.
minus 1.
Yep. And if it's P into P minus 1, then we are done. So we'll assume it's P minus 1.
So yeah, if it is like for both G and G plus P, like if any of them is P into P minus 1, then we know that it is the primitive rule. So we'll assume the order is P minus 1 in both the cases. Okay. Now, for
So
the
that
sake
would
of contradiction, uh, let us just assume K equals to P minus 1. So G
and
to the power P minus 1 is 1 mod P square.
yeah, and same as for G plus P to the P minus 1.
Yeah. Now, for like G plus P to the power P minus 1, we can expel it basically like G to the power P minus 1. What will be the second term of the binomial? Should be P minus 1
P minus 1
So
into G into P
G power P
into G
minus
to the
2
power pi
to
P
P.
minus 2.
and see that after this, all the terms will be divisible by P, right? Because here is a P, and all the next terms there will be P square, P cube, and under modulo P square, all of them will be like 0. So we'll not have to write those things.
Yes, we have
So
this
it,
relation mod P square.
yeah. And we note that G to the power P minus 1 is 1 mod, and this is also 1 mod. Like for the sake of contradiction, both are 1 mod. So this just cuts, and basically, and P square here cuts. So P minus 1 into G to the power P minus 2, this will be like
0 mod P.
0 mod P, which is not true because G is also coprime with P, P minus 1 is also coprime with P. So we are basically done. Did everybody understood the proof?
Yes.
Nice.
How did we reject K equals P into P1?
We didn't reject that. We wanted to prove, we assumed P minus 1 and we proved contradiction. If it is P into P minus 1, that is just phi of P square. So K is just primitive. That means G is just primitive root modulo P square. That is like we want to prove. That's why we assumed contradiction.
Oh, okay. Yeah, got it.
Okay. I'll just state a lemma because I don't have time much. I will not prove it now. You guys should try to prove this. It's not too hard.
Wait, does this use Hensel?
It doesn't.
Okay.
If G is a primitive root modulo P square, then G is also a primitive root modulo P to the power K. This is homework. Try this. And if you get solution, you can DM me in Discord. Do you want to do a problem right now? Or we can discuss some more theory?
Theory.
Oh, I didn't expect that, but I am happy with the answer. Okay, let's do a problem which is this is an easy lemma. I'll just take it in 1 minute probably. This is obvious, but okay. Like Sanskar told it before, if G is a primitive root, then G to the power K is a primitive root if and only if the GCD of K and P minus 1 is 1. And you will use this fact a lot of times in problems. This is a very important thing to remember. Why this is true? Like, it's just one liner. Like we have G to the power P minus 1 is 1 mod P. Like the order is P minus 1. And so you have G to the power K, say the order is something like T. You need this to be 1 mod P. What do you have here? That just means that P minus 1 has to divide, because this is G, so has to divide KT, but P minus 1 is just co-prime with K. So it will divide, wait. Yeah, so P minus 1 is co-prime with K, so P minus 1 will divide T. And so the order is T only. Order of Pg to the power K is T, which is P minus 1. So G to the power K is the primitive root. And if you did not have like some P minus 1 and K has some common divisor, which is D, then you can just choose to be like P minus 1 by D. And that D and D here will get cancelled out. And you will get like G to the power P minus 1 that will give 1 mod P. So other things will not be primitive root and only the things with GCD being 1 will be primitive root. I think this is clear. This is like very important. Like you should remember this fact. Not remember, but kind of like it should be intuition.
This also means there are 5 P minus 1 roots.
Exactly. This also means you have 5 of P minus 1 roots because if there is one root, then all the co-prime things are basically primitive root, G to the power something. So there is exactly 5 of P minus 1 primitive roots. Okay. Now let's do this.
The earlier proof, what exactly is T?
T is the order for G to the power K.
Okay, okay.
And we wanted to prove T is P minus 1.
Yeah,
And because P minus 1 divides T, T is P minus 1.
okay.
Just try to do this. I don't know if Mandar did this. This is a famous problem. He can do this in his class. I'm not sure if he did this or not. Did anybody see this problem before?
Yeah, Edmond.
By
Yeah.
the way, I have given buffer problems. If you guys have not taken screenshot, take screenshot. And if you're done with this problem with square free part, try to do in general. If you're done with square free. Like this also holds for general. Okay. I think everybody has taken screenshot. I'll just go down. Try to do this. This is more like a problem than theory, so I'll give you guys 5 minutes to try. At 7:43, I will like on my video and camera. Did I say video and camera? Any idea?
So for the case when p minus 1 divides x, it is trivial, right? So if we
True, p minus
if
1 divides 6 is trivial because everything is just 1 and you have p minus 1 mod p, so minus 1. True?
In the other case, just take primitive roots. Right?
If x is odd also, it's trivial because you can club the first and the last term.
But uh, try to think of the primitive root direction that we did.
Okay.
Like the set 1 to p minus 1 is exactly the set g to the power 1 to g to the power 6.
Yeah, so basically what we did at the first, we tried to remember that this 1 to p minus 1 set, this is like g to the power 1, g to the power 2 to g to the power p minus 1 set. And basically you have these things in powers. And when you have like same things in powers, you can try to think of primitive roots because that gives the nice value in primitive roots. So what you write as under modulo p, obviously, p minus 1x to the power x, this will just become g to the power x plus g to the power 2x plus dot 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 g to the power p minus 1x. Do you see why this is true, right? This is what I discussed earlier.
And now it's just gp.
Now it's just a GP series.
And common ratio
So
is
take
not
g to
1.
the power s x common, g to the power p minus 1 x minus 1 by common ratio is g to the power x. Okay, so g to the power x minus 1 mod p. Okay. And now,
This quantity is obviously like 0.
yeah, if like g to the power p minus 1, x is not p minus 1, so this downside is not equals to 0.
Yeah.
And the upper side is 0, so this is but 0 mod p just. Like the problem, if p minus 1 divides x is the like 0 by 0, which is not good. Like you can't tell anything. That's why we took p minus 1 not divides x. Then only the numerator is 0 and downside denominator is non-zero. So the total thing is 0 mod p. And if you have to like x to be some p minus 1 to the p minus 1 into something, then all the things are just basically 1 and you will have p minus 1 mod p. So that is minus 1 mod p, so you are done. Any issue with the problem? Anybody?
No.
No.
No, it's all clear.
Okay. Now I'm going to do one of my favorite things. Okay, I don't think we can do any problem today. Okay, probably one after doing these two things. The first thing is easy. Prove that the product of primitive roots is 1 mod p and sum of primitive root is mu of p minus 1 mod p. Do you know what is a mu, Mobius function?
Yes.
Yes.
Wait, can you tell me?
Okay, like you define mu to be like mu of n to be say if n is not square free, then mu of n is just 0. N is not square free.
For the second part, you can just take the Dirichlet convolution of the, like, define the sum of primitive roots to be f of p. So you can take Dirichlet convolution of f of p with 1, and that would give you the Dirac delta function because the sum of roots mod p is 0. And since the Dirichlet
Yeah.
convolution is giving you the Dirac delta function, therefore taking Mobius inversion would give you the Mobius function.
Mhm. That is one of the proofs, which I'll not discuss because I don't think everybody knows Dirichlet convolution here. And if n is uh, square free, n is square free, then it is just -1 to the power Pn, where Pn is the number of prime divisors. So something like 6 is like 1 because it has 2 prime divisors and it is square free. But something like 30, this is -1 because it has 3 prime divisors. And something like, I don't know, 12 is 0 because it is not square free.
Number of distinct primes or just
Yeah,
Aritra,
number of
can
distinct
you
prime
zoom it out a
divisors.
bit because things are not visible.
This is just the first thing should be easy. So try to do this first. If I don't do any problem today, I'll send the problem list in the Discord and you guys can try.
I think I solved. No, wait, no, never.
For
Did you
lemma
solve
1.8, like we can use two things. So either we could use that if G is a primitive root, then G inverse is a primitive root. So we are
Yeah,
done. Or we
basically.
could also use that all the distinct primitive roots are given by G to the X, where X is a number coprime to the P, and then we multiply them all. So this is just sum of all coprime numbers to P less than P minus 1, which would be P minus 1 into P
Both
pi
works, but
into
I wanted
e
to
to the
show
power.
the inverse idea basically. So just see that if G is a primitive root, then G inverse also is a primitive root. Why is this true? Sanskar or anybody else?
I mean, isn't this just the theorem that we just disproved?
Basically, so because -1 means like G P minus 2, and that is obviously coprime with P minus 1. And because that is coprime, that is a primitive root.
Like
And
G to the K and G to the minus 1 to the K are inverses. So G to the K is 1 mod P if and only if G to the minus 1 to the K is 1 mod P. Therefore, K
so
requires
basically we can make this sets that G comma G to the power -1 for all things. And if we just make a product of them, try to think why did the condition did not hold for 3 and only holds for P greater than 3. And if we like multiply all the G and G inverses, like G and G inverse gives 1 mod P. And if we take all those pair of primitive root and their inverse, because all of them are primitive roots, and we multiply them in this order, then we just get like bunch of ones, which totally gives 1 mod P. But why
you
doesn't
have
this work for P equals to 3?
I think maybe because G equals 1 by G, G inverse can.
Yeah. So in that case, we'll have G like this has to be distinct basically. And for this to be distinct, like this is G square 1 mod P, and that makes P equals to 3. So if we have P greater than P equals to 3, so if we have P greater than 3, then this can't happen. G can't be equal to G inverse. So that's why all the things are distinct. And if we multiply all the things and see if G, like, we know that inverse is like kind of bijection. So something like G inverse and some other G dash inverse can't be equal. And that covers the whole primitive root set. That's why the product is 1 mod P, and we also multiply all the primitive roots. I think this is clear.
Yeah.
Okay, now we'll do the sum. Do you want to do the sum or try on yourself and we can do some other problem?
problem.
What did you say, Adam?
Other problem.
Can you write in chat? I actually did not.
People are saying
Yeah.
another problem in the chat, so let's do that.
He said other problem.
Okay. So try this and okay, I'll post a solution. Yeah, I'll just paste some of it for now. Let's see. Easy problem or hard problem? Okay, let's do this. A medium. We have 8 minutes. Try this. I'll paste another problem. Hope we can do 2 at least today.
The problem is not visible.
But you can't see the problem?
No, like it's partially visible. Like, can
I
you
mean,
do
there
that?
exists a x, like it's just e here. Like there exists natural number n such that this happens if p is 9k plus 1.
Okay, okay. Try cube completion, I think. Then primitive roots.
Try this first and this second.
Yeah, that's what I'm saying. For the first one.
For the first one, what did you say?
Like we could try cube completion first. Like making a perfect.
Oh, like you mean cube completion?
Yeah, yeah.
Okay, not a bad idea. We don't have much time, so do you guys want to try more or should I explain it? I think I can explain one problem and this one you can try on your own. Like I don't think I have much time, so what do you say?
But that's a good idea.
I mean, you could give a hint to make it fast. rather than-
Okay, like obviously p is 9k plus 1 means like p is 18k plus 1 because
Mhm.
primes can't be even. At least like p if p not equals to 2, which it obviously isn't in this case. And try to think primitive roots. Like okay, that's like we are doing. So you will think primitive roots. What more hint can I give? Hmm.
I think we should try factoring n cube minus
Okay,
3n
I'll
plus.
just write the first line. You know that g to the power p minus 1 by 2 is plus 1 is 0 mod p
Right.
because like either this is 1 or -1 mod p, but this is not 1 because it can't be the order. Like order is strictly p minus 1. So you have this. And now
Now I
put
can just
in
hold
p
Q.
equals to 18k plus 1, you will get g to the power 9k plus 1 is 0 mod p. Okay. And this is the hint. Now, what do? You have g to the power 9k plus 1 to be 0 mod p. From here, what is the first step you should do?
I mean, it's AQ plus PQ.
Exactly. So
Just take,
g to the power 3k plus 1.
yeah,
Just see if
like,
I'm like factorizing correctly or not.
yeah, I mean, it's G to the 3k plus 1.
Now see if g to the power 3k plus 1 can't be 0 mod p, because that means g to the power 6k is 1 mod p. Do you see that?
Yes, yes. So it's not 1.
So we'll have g to the power 6k minus g to the power 3k plus 1 to be 0 mod p. Okay.
Can you explain again why g to the 3k plus 1 isn't 0 mod 2?
Sure. So g to the power 3k 0 mod p means minus 1 mod p, right?
Yeah.
So g to the power 6k is 1 mod p.
Oh, okay.
So
Yeah.
the order is like
Okay.
6k, but we want the order to be like 18k because g is the primitive root.
Yeah, I got.
How do we say that g to the power 3k plus 1 has no common factors with p? Okay, I'm sorry.
That's what I proved, right?
Yeah.
And basically that is, see here you have nq minus 3n plus 1. And we magically are trying to get of this form, basically doing some manipulation here. So
Yeah.
we still didn't get the form. What can we do more to get the form? Like the square completion idea. Now, not
Yeah.
square, cube.
Cube
So can we do
completion.
some algebraic manipulation?
Okay. So
Like you have n cube plus 3n plus 1.
yeah, so like take maybe G to the 3k to the other side and again apply Q plus PQ.
That might work, but is there anything, like, do you get anything concrete from there?
Probably no.
Hmm.
Can we look at g to the power 2k plus 1 whole cubed?
G to the power
2k
I,
plus 1 whole
whole
cubed.
cube. Sure, that will give us like g to the power 8k plus 3 into something, but like there will be square term. Like, will that help us really?
Wait, where did 8k come from?
Like you're trying to make of this form, right? In the form of the question.
Yeah.
But there will be like square terms and like also like plus 1 will give a like plus sign. Like I don't really see how can this help. This might help, I don't know, but I don't see it at least. Okay, like you have liberty over only n, right? So you want to make it probably more like you have probably more freedom in that word. That is probably not the right word, but let's try to
Maybe
think a bit
try setting L to be
backwards.
something, right?
What can we do in the backward step to get this basically?
Like n equals g to the power 2k looks nice.
How does it exactly look nice?
Because the plus 1 and the n cube matches, only the minus 3n is different.
But the square term is there. How will you remove the square thing?
Um,
Okay, so maybe we would set n equally k plus 1 or something.
Yeah. So we'll set something, but let us just set n equals to x plus y for now. We'll probably like not use the whole x plus y condition. We'll probably make y equals to 1 or x equals to 1 or something x equals into y equals to 1, something mod p.
why
But
x
we don't
plus
know what
1?
we'll use now. So we just put n equals to x plus y to see again what?
I mean, x
Uh,
plus 1 just makes it.
No, I'm just putting x plus y. We'll probably not need the whole condition. We'll probably do some more condition on x and y
Sure,
later.
sure. Okay, okay. Yeah.
But I'll just put to see backwards, like what happens. I'm actually doing backwards. Like if you see, I assume nq minus 3n plus 1, and I'm trying to working backwards. That putting n equals to x plus y, will that give us something? If we take some other condition, probably that holds. That probably we don't know of right now. So what does give us? Okay, I'll just remove this. X plus y whole cube minus 3 into x plus y plus 1. And obviously we need all the things in mod p. So don't forget that. We are trying to deal with mod p. I mean, I get it that x plus y, putting n equals to x plus y is not that motivated, because why will you put just n equals to x plus y? But trust me, it will help. What do you get after solving? Do I really have to solve right now?
I mean, it's x cube plus y cube plus 3x square y plus 3xy square minus 3x minus 3y plus 1.
Putting y equals to 1 may help.
Sure.
Okay.
Let me try something more. Wait, not more. Plus 1. This is mod p. See this term. This is like kind of. This thing is kind of like annoying. Can we make it like 0 somehow without not changing much?
Yes, you can make it 0.
X equals y inverse.
Yeah. So basically take xy to be 1 mod p.
Oh,
So
so
x and
should
y
we
to be
put
inverses.
like n equals g plus g inverse?
Exactly. So we just put x and y to be their inverses. And then if we do this, so x cube plus x inverse cube. Writing x to the power minus 3 is okay. 1 mod p. And see how this directly finishes the problem.
What had we got originally?
We want this to be 0 mod p. We have this to be 0 mod p.
Yeah, so this
Like
just
we don't
gives
have,
it.
like we need this to be 0 mod p. And we have this to be 0 mod p. Try to like relate. These two things are like super close if you see.
Yeah, just x is g. Because like
What
multiplying
is
by k
x?
cube won't affect the condition, right? So it's just.
Yeah, now the thing that Arab was saying, that g to the power 2k, now it does help.
Like you could just divide by G, like where the condition we got. We could just divide by
Mhm.
G to the 3k.
Yeah, now g to the power 3k. Sure.
Yeah,
Just put x to the power g to the power 2k. Okay.
I guess G to the power k, right? Not G to the power 2.
No, we want 6k, right? That's why we're putting 2k because we want here 6k.
No, but then we'll get minus 6k there. I guess we
Yeah,
should
but
put
here the sign is minus and g to the power 9k is minus 1. So if we like divide by 9k, that will flip the, like that will be 6k will become like minus 3k
Oh, okay.
and the
okay,
sign
okay,
will
okay.
flip.
Okay,
You
sure.
see that why I'm doing that. Like
Yeah,
the coefficient for these two things are matched. So I want to match this first and then I will see what can I do with the rest of the terms.
okay.
So that becomes like g to the power 6k plus g to the power minus 6k plus 1. But we know that g to the power 9k is like minus 1. So if we just multiply g to the power 9k in this thing, that is like minus g to the power 3k plus 1 mod p. And we know this is 0 mod p. So this is also 0 mod p. And we got a construction. What is the construction? N is equal to g to the power 2k, where j is a primitive root, plus g to the power minus 2k. But like you will never think of this at first. So by kind of doing like this, you get the construction. This works.
But why
I think we
x
have,
plus y? N equals x plus.
we're just like, we can't do anything more. So let us just explore putting x plus y and then see if we can make some other, like we got an equation. We can put some other condition to make some terms vanish and that will probably be nice. It's just like being hopeful and putting something and hopefully it works out. Like obviously you will not think of x plus y at first, but if something doesn't work, like let's just put x plus y, probably we can make something x and y such that it is good.
Okay, yeah.
Wait, can you show the proof again? The bar part.
Did you understand till x plus y part?
Yeah, I understand.
So I did the calculation and I made xy equals to 1 mod p. So x and y to be their inverses modulo p. Okay.
Yeah.
Now I put x equals to g to the power 2k because what I want this thing and this thing to be same because I know this thing is 0 mod p for sure. So because I have x here and here g to the power 6k I have, so I just put g to the power 2k such that these two terms match. So I get g to the power 6k plus g to the power minus 6k plus 1 to be more plus 1 mod p. But I know that g to the power 9k is minus 1 mod p, right? So I can just multiply for only this part. I multiplied g to the power 9k. So that g to the power minus 6k is just minus g to the power 3k plus 1. And we know that this is 0 mod p. That's why this is 0 mod p. And because this is 0 mod p, this thing is 0 mod p, like the n cube plus 3n plus 1, this is 0 mod p. And this is what we needed, that there exists some n. And the n is this, g to the power 2k plus g to the power minus 2k.
Makes sense, makes sense.
Sure. I don't think I can do any more problem. Take the screenshot of this. This I think you have already taken screenshot of the first problem. Take screenshot of this. I will post a PDF with the solutions. Or like probably tomorrow or day after tomorrow, you guys can send me solutions if you do in Discord DM. Have you taken a screenshot? I hope so.
Yeah.
Okay. And this is, I think you have also taken a screenshot. So this to our homework, I will send more problems when I like compile the PDF and stuff. So I think that is it for today. Any doubts with any of the problems, the proof for any of the part? Oh, I didn't discuss this part. I will set the proof for this. I'll write the proof, and if you guys have any doubt with the proof, you can DM me on Discord. The summation G part. Okay, I think that's it for today. I'll try to stop the recording.
Bye. Thanks.
Thank you.